Hi, I'm Luke McKinney, Course Cram's Physics 117 and 118 instructor. It's time for forces. We'll be doing Newton's laws 1, 2, and 3 and showing how to draw a free body diagram, which you need to solve almost any force problem.
What is a force? A force is something that can cause an acceleration. And we remember an acceleration causes a change in velocity. And we saw in the previous primer that a change in velocity can mean speeding up or slowing down or just changing direction. But what does that mean? Well, it means if you've no forces, you don't have any acceleration. Let's think. If we have just a nice little mass sitting there on its own, doing nothing, like Luke Skywalker between movies, if there's no force acting on it, it won't accelerate. So it'll just sit there happily forever. Or another case, if you have a mass flying through deep space with a certain velocity, which you know to some sounds horrifying, but honestly often sounds peaceful. If it's flying along with a certain velocity, if there's no external forces, then there's no acceleration. So that velocity won't change. It'll just keep going on forever and ever the same with no acceleration. And this concept is Newton's first law. If there's no external force acting on something, then there'll be no acceleration. Its velocity won't change. So the acceleration is zero, and this is very often called equilibrium. A key word we'll meet. You can have static equilibrium when it's just sitting there, or dynamic equilibrium where it's moving, but the acceleration is still zero. This concept is also sometimes called inertia, the idea that if something has no external forces acting on it, it won't accelerate. And these do have to be external forces. If you think about anything being accelerated, it can't do it all by itself. For example, my box flying through space, it couldn't accelerate itself from the inside, no matter what. It can't just psychically will itself to the side. If it wants to change velocity, it needs to hit something or be touched by something or throw pieces of itself away like rocket fuel. And that's Newton's first law. The second law is where we bring an equation into it. And again, remember, equations work way better if we say them as words instead of letters. Like this is just sigma f equals ma, which sounds like that wouldn't even be useful as a password because you can't use Greek letters on most keyboards. It's the sum of all the external forces is the mass times the acceleration. Now, once we got an equation, we'll want to look at the term. Force is a vector, which means it's got a size and a direction, and it's measured in newtons of n, newtons. And in an equation like this, we'll often break things up into x and y. We remember how to do that. If we have a force at some angle to the horizontal, we can break it into the horizontal component, which is the force times the cosine of that angle, and the vertical component, which is the force times the sine of that angle. And then we can do our force equations in x and y, and that's how we'll solve the vast majority of any of these problems. Other things, we've got this idea of an acceleration, which means we're going to hit a keyword that comes up quite a lot. If a problem says equilibrium, as we saw in the first law, that means the acceleration is zero. Another way they can say that is if they say constant velocity. If a problem says constant velocity, well, that means it's not changing, which means the acceleration is zero, which very commonly means you're going to be using this equation with acceleration of zero to solve the problems, which is pretty useful. Finally, we have Newton's third law, the most action movie of all the laws. For every action, there's an equal and opposite reaction, which could honestly work as the final line for any one of those Explode Things movies, which is weird because those movies always wildly violate the laws of physics in every other way. But the idea is that if A exerts a force on B, B exerts an equal and opposite force on A. In math, you can just write that down. The force of A on B is the opposite, because in physics, plus and minus are just directions, minus the force of B on A. But that really doesn't actually help us much in terms of picturing it. The key way is, well, whenever you've got two blocks pushing on each other, this will work. For example, if the top block is pushing down on the bottom with 100 newtons, the bottom block will push up on the top with 100 newtons. So that's how you move around problems with more than one block. But the more interesting examples is it's how we move around and do things. Like, for example, let's say I'm here and I'm going to jump up in the air. Hooray! Well, I kick down with my legs. Now, how on earth does that actually make me move up into the air? I'm pushing down with my legs. Well, the idea is the ground exerts an equal and opposite force on me up. And that force is now greater than my weight, which we'll see later. And that's what boosts me into the air. That's also why I can't do a nice double jump to reach some coins up there like Mario, because now if I'm in the air and I kick down, I have nothing to kick against. So there's no Newton's third law to push against, to push back up against me. Another example, the Earth and me. Hello again. I'm very narcissistic today. Now, if I feel a weight of 800 newtons pulling down on me, remember, forces are vectors, so they have size and a direction that can be drawn as an arrow. Then the Earth feels an equal and opposite force pulling up on it of 800 newtons. And this is true of every possible scenario, no matter what. There's two ways this law can be dressed up. The first is the idea of trying to make it look ridiculous. Now, what do I mean by that? Well, let's say you have a 16-wheeler truck loaded with anvils going down the highway at 30 meters per second, and a fly hits the windscreen. Now, the fly exerts a very tiny force on the truck. What force does the truck exert on the fly? Exactly the same size of force. It's always equal and opposite. It doesn't matter how big one is and how small the other is. It's the idea of the force is the same size in each case. Now, why does it go so badly for the fly compared to the truck? Well, Newton's second law can tell us that. The force is the mass times the acceleration. So if I rearrange that, the acceleration is the force divided by the mass. So in that case, the acceleration on the truck would be the force divided by some great big number. So you'll get a very tiny acceleration. The acceleration on the fly will be the same force, but by some tiny divisor there. So that'll make the acceleration so much bigger for the fly based on the same force. That's what mass actually is, by the way. This isn't just some weird little effect of it in an equation. Your mass is a measure of how hard you are to accelerate. It's basically a constant in the equation, and we all have one. So that's an amusing one there. The second way the third law problem can turn up nicely is buried in numbers. And what do I mean by that? Well, you can get something like you've got block A and block B, and the force of A on B is 10 newtons. And you're told A is 15 kilograms and B is 7 kilograms, and they're moving up the slope together at 7 meters per second, and the slope is at 10 degrees, and there's friction, and there's all sorts of other stuff going on. And you're asked, what is the force of B on A? Well, Newton's third law overrides everything else. If the force of A on B is 10 newtons, then the force of B on A is minus 10 newtons, or just 10 newtons if they were only asking for the size. It doesn't matter whether B is being moved or not. It doesn't matter whether A rams into B and stops and squeezes, or if A is pushing B up, or if B is pushing A back down. The absolute key of Newton's third law is for every action force, there's an exactly equal and opposite reaction force between the same two objects, no matter what else is going on. And you can always count on that. A free body diagram is a diagram of an object or collection of objects with only the external forces acting on them. It's also basically the key to answering loads of different force problems. We've already got the equation. The sum of all the forces is the mass by the acceleration. And we know we're probably going to break that up into x and y coordinates, which is usually a pretty nice hint we're going to need a diagram with x and y. And the idea is you just draw the one object or collection of objects and the forces acting on it. And that's what makes things a lot simpler to deal with. We haven't actually met these forces in the primers yet. We're going to see that in the next one, but we can just show a little sort of example, like if we have a block being dragged along by a rope, we would see that the object has a weight, a tension, a normal force with the ground, and maybe some friction with the ground. And we'll see all those in the next video. Now that looks pretty direct. It's just the object we were looking at. But the idea that can come more into it is if you've got a bigger collection of objects, it becomes much easier if you break things up in terms of the free body diagram of just one of them. For example, we have a bar and a pin on a block, another block, and a block with a rope. So that's A, B, C. Gosh, doesn't that all look big? Well, if we just look at the free body diagram of B, it has the weight of B acting down. A is pressing down on it, so there's a normal force between them. And C is below it, so there's a normal force pressing up on it. And that's all. We don't have to deal with all the other parts in this diagram. And we would do a diagram like this for each of the blocks. And we'll find those are all much simpler ways of dealing with the problem.
Well, I hope that video was useful. What's even more useful is more videos, and you'll find plenty more in the playlists here. But even more useful than that would be a live session with lots of focused practice, the ability to answer your questions, and then doing lots of exam-style practice with focused example problems and full solutions. Because that's what we do at Prep 101. So make sure to join our Prep 101 Study Hub Facebook page, where you'll get details about all the sessions, some of them are even free sometimes, and other resources that'll help you to do better on your exam.